So welcome to lecture 3 of the course. Today we'll start dealing with some of the foundations, the theoretical foundations that we need in the course. But before I do that, let us recap some key concepts from the last lectures and then talk about the concepts I want you to remember from this lecture. So in lecture 1 and 2 we talked about diffraction. We could see how diffraction leads to image degradation by cutting out information from the sample that isn't captured by the numerical aperture of the objective lens. We defined, at least qualitatively, the point spread function and the optical transfer function, which quantify how information is lost. So if I have a point, the point isn't in the sample plane, this point isn't imaged as a point, it's imaged as a blob, and that blob is called the point spread function, and that leads to loss of resolution. An alternative way of thinking about this is to think about the sample content in terms of spatial frequencies. High frequency detail corresponds to small sample spatial detail, and so if the numerical aperture isn't able to capture the high spatial frequencies, that leads to information loss. And so OTF and PSFs are alternate versions of the same thing, really. It's just for some concepts it's nicer to talk about spatial frequencies, and in others it's better to talk about the spatial coordinates of the sample. Finally, we talked about the numerical aperture, how it determines image resolution. We talked about contrast also being important. If I have a sharp, highly resolved image, that's no good if the image is flooded by light, out of focus light that I'm not interested in. One method, one of the most important methods, is the confocal microscope that enhances image contrast by rejecting out-of-focus light, in fact by the use of a pinhole. We saw that the trade-off that we have is that what we gain in contrast we lose in imaging speed, because now we are restricted to imaging only a point at any one time. That in fact turns out to be a general principle. There are trade-offs in microscopy. I can increase resolution, I might decrease contrast, or I might decrease imaging speed. Or I might be able to increase contrast, but I have to sacrifice imaging speed. So it's those trade-offs we need to make to apply the right techniques for the right practical application. I talked about microscopes, what they look like, and we talked about two techniques that are frequently used. The bright field microscope, where you get a low contrast because of the background that's produced by light that isn't refracted and isn't containing information, and fluorescence, which gives you very high contrast because the light that isn't exciting the sample, the light that doesn't generate a fluorescent signal doesn't make it to the detector because of the different color, which you can filter out. And finally, of course, we've mentioned this, you need to provide magnification, resolution, and contrast to get good images. So that's the key to the course. So in this lecture, what we want to do is to look at this problem of diffraction, which is central to this course, in some detail, where it comes from. And to understand that, we need to understand a little more about the wave nature of light. And so we will briefly talk about the wave equation. I don't expect you to remember all the details or to use those in exams. It is an understanding I want to generate, so you see where things come from, so that you can apply the results in the correct way. We will introduce concepts such as the wave vector and frequency, and see that these two quantities describe how the electric field of a light wave oscillates in time and also in space. And so the wave equation describes that precisely. And then we will talk about the two types of waves which are solutions to the wave equations, which are the only types of waves that you need to know in this course. The plane wave and the spherical wave. I've drawn pictures of this already in the first lecture, and here we just write down what the equations for those are. And then finally we talk about the key point about what causes diffraction, namely it turns out the wave equation is a linear equation, and so therefore the principle of superposition applies, and so different solutions to the wave equations can be added to generate new solutions. And so this leads automatically to the problem of interference, and we get constructive and destructive interference. And of course, for image information, how the light waves add up is essential for us to understand how images are formed, because that is at the heart of what goes on in the diffraction process. So the lecture notes are pretty self-contained for this part of the course, but what I'll do is I will take highlights from the lecture course and write on paper to do the talking whilst I'm writing, so I have the right speed for you to understand the key concepts, and then you can look at the details and go back to them by referring back to the notes. You will identify what refers to what.